Hello, my name is Ros Gillis and I'm here today to talk about feeding animals from the sea, cattle foddering at Neolithic Jarlshof. And I hope today that you will learn something about how Neolithic farmers adapted to their environments and adapted their animals to their environments to feed them and also to feed their communities. Now, the Shetland Isles represent the outermost edge of the Neolithic expansion that started off in the Anatolia. Then these communities moved into the Balkans, through Central Europe, the bogs of Hungary, into Northern Europe, and finally into Britain, and also along the Mediterranean coast, Portugal, and then up the Atlantic coast into Ireland and Britain. And along this journey, they adapted to different environments, to different landscapes, from from the boglands of Hungary, northern Hungary, to the more dense forested landscape of Alsace, into sort of the more open woodland that you might find in Britain. And at the same time, they're sort of going through different climatic zones, which would have resulted in them adapting their plants to new environments, and also their animals to these new environments. And along this journey, milk would have provided an important source of protein and fat, and could be dried and saved and stored for during hard times and during crop failures. But Shetland was finally settled by these Neolithic farmers by the mid-4th millennium BC. Now, Jarlshof has been excavated several times over the last 100 years, and it's really a palimpsest of Neolithic, Bronze Age, Norse, medieval, and in the more recent times. Midden too, rather unexcitingly named, was the earliest evidence of activity and was excavated by Gordon V. Childe. And here he is with the excavators at the site in the 1920s. And the material from the Midden dates around 3000 BC. Stable isotope analysis, basically the difference between heavy and light isotopes of a particular element, such as carbon, oxygen, and nitrogen, can provide us insight into animal and human diets. And from this, we can interpret about human, environment, animal dynamics over time and space. Sequential analysis, so that's taking a little sample of the tooth enamel particularly from cattle or sheep teeth, can provide a seasonal perspective at the time of that tooth development of the animal's diet. And the two main isotopes that we examine in tooth enamel is oxygen and carbon isotopes. Now, oxygen isotopes, the lighter isotope, which is oxygen 16, evaporates in the summer, and during the winter there is more oxygen 16, and so the isotopic ratio is lower during winter. Carbon, on the whole, in temperate European environments is fairly lax in variability. However, it can change. It can vary if an animal is eating, say, leafy hay during winter, or, for instance, aquatic resources. Now, generally, pastoral sources have a carbon value of around -26 per mil, whereas aquatic resources will have something much more higher, between 21 and 30 minus. Now, stable isotopic analysis has been used to great effect in to study animal husbandry in Northern Isles. And we know from ethnographic evidence that seaweed was being fed to cattle and sheep in Orkney and in Shetland. And modern sheep, which are renowned and prized for their excellent meat, the North Ronsi sheep, have been used to as a reference, to create a modern reference to investigate Neolithic sheep management. And the main researcher involved in this is Mary Ballas at the National Museum of Natural History in Paris. And she uncovered with collaborators the earliest evidence of sheep eating seaweed from Papua West Strait. And here you can see in the black dots, the higher values occurring when the white dots are low. So this is the white dots are being oxygen, and then they're low. So this is representing winter, and and the carbon is suggesting that this animal is eating quite a source of fodder that is very high in carbon, has a very high carbon value in comparison to those sheep from Napa of Howard, who from the black dots you can see that there's little variation at all. So we did the same analysis of cattle teeth from Golden Child's excavation, and we found that most of the teeth were typical of an open temperate environment. However, one tooth suggested that during winter it was consuming a plant source that had a relatively higher carbon value. And when we compared this to the Papua West Strait range in values that they got from those sheep, it would suggest that seaweed is being consumed during winter. So what we decided to do was, observing the teeth had these thick deposits of coronial cementum, which accumulates throughout the lifetime of the animal. And you can see it here, this sort of creamy stuff, thick creamy stuff, and then there's a selection of teeth there. And some of it even had waves within it. It's mainly collagen, and it's a valuable source of biomolecular information such as ancient DNA. Now we carried out an experiment of compound-specific stable isotope analysis, and because we were looking at the source of plants in an animal's diet, we targeted N-alkanes. Now N-alkanes are hydrocarbons. They're resistant to biodegradation. They provide a valuable molecular marker of the plant origin, and when preserved in organic matter. And the carbon skeleton, basically the long chain of carbon molecules, and the length of these carbon molecules can be identified as source of plant materials. Now the Cmax value for seaweed sort of ranges between C15, C17, and C19. However, for seagrass, it's actually much higher, and it goes from C21 to C25. Whereas for terrestrial plants, you're looking at C29, C31. So if we find peaks on a spectrometer around C21 and C25, it suggests that alkanes are preserved from seagrass. So the compound-specific analysis of the dental cementum was carried out by Natalia Eggers at Laguna University in Tenerife. First, the cementum from the teeth was sampled. Then a total liquid was extracted. Then they extracted the N-alkane, and then the N-alkanes were injected into the mass spectrometer. And then from this, it's put through a gas chromatography mass spectrometer, which separates out the component parts, and then there's an isotopic ratio mass spectrometer that measures the weight of the carbon isotopes of these specific compounds, and then you get a final resulting chromatogram. Here we have the results from a spectrometer output from one of the two teeth, and the range in alkanes that it shows up, go from C17 to C25. with a Cmax of about C21, suggesting that seagrasses are the main source of alkanes within this cementum sample. So next we did the compound stable isotopic analysis of the alkanes. Now seaweeds have normally have a value of minus 22.8, and this was based on a study done in California. However, our sample, the carbon value was between minus 31 and minus 35. Now, the Northern Isles is not California, and so this lower values that we're observing in our data may be a reflection of latitude. It also may be a reflection of lower sea temperatures, and lower sea temperatures can impact the plant productivity of seaweeds and seagrasses during winter, and result in a depleted carbon value in plants. So this begs the question, is this winter foddering with seagrasses? So our main conclusions are from this material analysis of using stable isotopes and compound specific isotopes, is that from the incremental we get a marine influence fodder source during winter, but only a slight indication. And however, from the dental cementum, it appears that at points in the lifetime of these cattle, that seaweeds, seagrasses were being consumed during winter. This is still very preliminary data, and there's much more analysis that needs to be carried out to fully verify these results. But however, what I think it shows is, and I think this study shows, is the adaptability of Neolithic farmers. And the next question is to understand, is this a deliberate strategy? Did they collect seagrasses and seaweeds and then supply it and dry it and then supply it to their animals? Or was this part of a more extensive management strategy where the animals were allowed to roam because there wasn't actually that many predators, and the only thing that could happen to them is they fall off a cliff? And this is something that hopefully we can examine in more detail. The main problem in Shetland and across a lot of Scottish contexts is the poor preservation of bone. However, with organic residues and the fats that come out of that, we can actually investigate, because these fats are coming from the animals, we can investigate fodder practices through these fats. And now through Lucy Cramp's work and Oliver Craig's, we now have like a wide data set that we can actually start investigating, together with the stable isotope work that has been generated by Mary Belas, Jennifer Jones, Jackie Malville, Richard Madrick. We have a multitude of data out there to really analyze and start pinpointing different strategies in different environments in Scotland. And really, I think this will enhance not only just Neolithic research in Scotland, but through time. So I really like to thank the organisers and thank my collaborators, Tapila. I did learn Gaelic a long time ago at primary school. This study would not have been possible without Alison Sheridan and Jerry Herman, and to my collaborators Natalia Gez and Cheryl Makarovich at Keele University. Thank you very much.